All right, hello everybody and welcome to our video today where we're talking about general chemistry, chapter 3, bonding. So we're going to start out with some pretty basic concepts. Again, this is just a review of something I'm sure you've already learned at this point. If you have not heard of the things I'm about to, generally gloss over, then I would definitely recommend looking at further videos in more detail. But just, make sure we get all the terms covered that was discussed in this chapter. So we have covalent bonds, which is the sharing of electrons between atoms of similar electronegativity. And the sharing of electrons. The sharing of electrons piece is really important because for ionic bonds, there's actually a transfer of electrons. So the sharing of electrons between atoms with similar electronegativity is very important. Another important note is that as you increase the number of bonds, so from single to double to triple bonds, the strength increases, which also increases the energy, but the length of those bonds decreases. So a triple bond is shorter than a single bond. Next, we have nonpolar, which you would have a change in electronegativity, or a difference of electronegativity between the two atoms that is less than 0.5. That would lead to nonpolar, okay? Polar, if you were to attach a numerical value, it would have, the two atoms would have an electronegativity difference between 0.5 and 1.7. So again, these are the numerical values. For me personally, a lot of the time I looked at the atoms, see, generally where there's a partial positive, partial negative charge. But if you did want to put a numerical value on it, this is, technically, I guess, behind the scenes, how that is really figured out. Then we have coordinate covalent bonds, which is the number of atoms, is when one atom provides both bonding electrons. You have ionic bonds, like we said, which is the transfer of electrons. We have cations, which is positive charge. Anions are negative charge. Then you have crystalline lattice, which is a large organized array of ions, for example, that we see in diamonds. Another piece up here, is the formal charge. And the formal charge equals the valence electrons minus the number of sticks minus the number of dots. And when we say sticks and dots, the dots are the number of non-bonding electrons. The sticks are a pair of bonding electrons, okay? So if you were to draw out the molecule, the formal charge would be the valence electrons minus the number of sticks minus the number of dots, okay? And another thing that you see here, so if we just have a single bond, okay, it's one sigma bond. If we have a double bond, there is one sigma bond, and one of them is a pi bond. And if you have a triple bond, we have one sigma bond and two pi bonds. So next, we're going to look at the types of intermolecular forces. Intermolecular forces mean between different molecules. So we have hydrogen bonds, which can only be done through hydrogen fluorine, hydrogen oxygen, hydrogen and nitrogen. So hydrogen bonding is fun, okay? Then we have dipole-dipole, which is if we have one water molecule here, one water molecule here, the oxygen has a partial negative charge where the hydrogen has a partially positive charge, right? So this creates temporary dipole moments in this molecule that we have an attraction between this partially negative oxygen and this partially positive hydrogen. So there's that bond right there. That is a dipole moment. This is really, it is between oxygen and hydrogen. So that is hydrogen bonding specifically, but this is just, how dipoles are used. Then we also have London dispersion, which are just, temporary charges within the molecule, very quick, nothing really permanent, and those are relatively weak bonds in comparison. And hydrogen bonds are the strongest. So now we're going to look at VSEPR theory. So one is the VSEPR theory for electron geometry, and one is the VSEPR theory for molecular geometry. One is for electron geometry, the other is for molecular geometry. And so when we're looking at the electron geometry, the bonded electrons and the lone pairs are treated as a region. No matter if it's lone pairs or, bonded electrons, each of those things is considered a region. Okay, so we're going to look at this example, well, through this chart, sorry. So if we have regions of electron density, so if we have two regions of electron density, we're going to have sp hybridization. This is linear, is the name of the electron geometry. And the angle that we will have, the bonding angle is 180. If we have three regions of electron density, so if we have 1, 2, 3 regions, right? Let's say, you know what? Let's say this is actually lone pairs and this is, you know, connected to something. This is a bond and this is a bond. This is one region, this is one region, and this is one region. Okay, so that's 3 regions of electron density. Yeah, that means it's sp2 hybridization. This is a trigonal planar, and the bond angles are 120 degrees, okay? So again, that was just an example just to show the electron density regions that we're talking about. Next we have, if we had 4 regions of electron density, right? So if we had a carbon, 1, 2, 3, 4, for example, 1, 2, 3, 4 regions of electron density, it would be sp3 hybridization and would be tetrahedral electron geometry with bond angles of 109.5. If we had 5 regions of electron density, we would have sp3d1 hybridization, and you can also count it as s1p3d1. So if you were to count 3 plus 1 plus 1, that's 5. So that's how you would know the 5 regions of electron density. If there was 5 of those, it would be sp3d hybridization. And this would be trigonal bipyramidal. And the bond angles are 90, 120, and 180 at this for 5 regions of density. And then finally we have 6, hopefully you can see. And then we have 6 regions of electron density, which will lead to sp3d2 hybridization with octahedral electron geometry with 90 and 180 bond angles. Now, I would definitely recommend understanding why this is the case, and also you kind of need to memorize, you know, the bond angles that go with each of these things as well as their name. So when you're looking at an atom or a molecule, you'll be able to tell what electron geometry it has. So next, we're going to take a look at the VSEPR theory for, I'm going to bring it a little closer, for molecular geometry. So if we have electron groups around a central atom, so if we have 2 electron groups around this central atom and we have no lone pairs, that means that it will be linear. So you just have a very straight, you know, that would just be very simple. But if you have 3 electrons, okay, and these again are the regions, however, the lone pairs, the number of lone pairs actually changes the name of the shape. So that's the difference, okay? So then we have 3 regions, right? And if it has no lone pairs, so if we had nitrogen back where we had it, right? If we had, and that's where these 2 things differ. So if we had nitrogen and we were just saying, you know, 1, 2, 3, that means nitrogen has 3 areas of electron density, right? 1, 2, 3. And no lone pairs, then that would be trigonal planar, okay? But if we had something like H2O, right, this would give us a bent. This would give us a bent H2O. Now I am jumping ahead here with this example, but it'll bring us to our next one. So we have 1, 2, 3, 4 regions technically, right, of electrons, but we have 2 sets of lone pairs. So we have 4 regions, 2 lone pairs. So if it had 0 lone pairs, it would be tetrahedral. If it had 1 lone pair, it would be trigonal planar. If we had 2 lone pairs, which we have, we bent. So H2O has bent geometry, and that's how you can tell that when you draw water, it needs to be drawn this way, okay? So I will go back to the 3 density example because I did jump ahead on that one. So if there was 3 electron groups around the central atom, if there was 0 lone pairs, it would be trigonal planar. And if it was 1, it would be bent. So again, all of these, with these names, the molecular shape names are the same as the electron geometry names when you have 0 lone pairs. So linear, 0 lone pairs, linear, right, for 2 regions. For 3 regions, it's trigonal planar if you have 0 lone pairs, 3 trigonal planar. Okay, so the first name of all of these regions for molecular geometry are the same when they have 0 lone pairs compared to the electron geometry, if that makes sense, okay? But otherwise, if there are lone pairs, you kind of need to change, and that's why I kind of underlined those ones, because those are like the basics, the originals. But if you do have some of those regions being taken up by lone pairs, you need to change the name. So let's go to the example with 5 regions. So if there's 0 lone pairs, it would be trigonal bipyramidal. If we had 1 lone pair, 1 group of lone pairs, we would have a seesaw shape. If we had 2 lone pairs, we'd have T-shape, and if we had 3, it would be linear in molecular geometry. And finally, if we had 6 regions of electron density, and we had 0 lone pairs, it would be octahedral. If we had 6 regions of electron density and 1 pair of lone pairs, it would be square pyramidal. And if we had 2 lone pairs, it would be square planar. Okay, so I know there's a lot of definitions of words, but I really, really would recommend learning this order. You know, if you have 0 lone pairs, it's this. If you have 1 lone pair, it's this. If you have 2, it's that. So I think that order and the names are really important. If you have any questions, please put them below. But otherwise, get to memorizing these, shapes and the names and the number of lone pairs and the number of regions and the bond angles. Put your questions or comments below, and we'll see you in the next video.